Welcome to today's deep dive. We are thrilled to have you with us because today our mission is to decode the complex, highly specific, and honestly, often counterintuitive world of enterprise firewall configurations.
Yeah, it's a topic that sounds incredibly dry or intimidating at first glance, but once you start to understand the underlying logic of how these systems make decisions, it becomes fascinating. It's essentially a high-stakes puzzle.
It really is. And to figure it out, we're looking at a really robust stack of sources today. We have official Broadcom and Symantec Endpoint Protection, which is often referred to as SAP documentation.
Right, the SAP docs.
Left detailed technical notes on firewall logic and VPN configurations, and some fantastic best practice guides from Watchpost Security.
Which are great.
And to you listening, whether you're an IT admin who spends your days actively configuring these networks, or you're just a curious learner sitting at a coffee shop wondering exactly how your work laptop stays secure on public Wi-Fi, this is going to be incredibly relevant.
Oh, absolutely.
We want to give you a major aha moment about how network security actually functions behind the scenes. It's almost like peeking behind the curtain of a magic trick, only to find out the trick relies on rigorous, ruthless logic. Okay, let's unpack this. We need to start with the core logic of firewalls.
Yeah.
What is the absolute golden rule here?
The golden rule, and really the fundamental mechanic of the Symantec Endpoint Protection firewall, is what we call the first match principle.
First match.
Yeah. You have to imagine the firewall reading its list of rules sequentially. It starts from the very top of the list and works its way down to the bottom, one by one.
So it's essentially reading a checklist, evaluating every single packet of data that tries to enter or leave your computer.
That's the basic idea, but here is the critical distinction that trips up a lot of people. As soon as a packet of data triggers a match on that list, whether that specific rule says allow or block, the firewall executes that action immediately.
Right.
And then it completely stops evaluating any rules below it. Subsequent lower priority rules are simply not inspected.
It just abandons the rest of the list. It finds an answer and says, my job is done, regardless of what nuance might be written further down the page.
It does not care at all about the rest of your carefully crafted policy. Once it finds a match, its job for that specific packet of data is finished.
Which perfectly explains this highly relatable, hypothetical disaster that jumped out from our notes. Let's walk through it. Imagine you have a junior IT admin setting up a new network, and they are tasked with ensuring maximum security.
Always a dangerous task.
Right. They're thinking, I need to lock this entire environment down. So logically, in their human brain, they put a block all rule at the very top of the firewall list. Position number 1, block absolutely everything.
Right.
Then, underneath that massive block rule, they painstakingly list out all their individual allow rules for the specific things the business actually needs to function.
It's a perfectly logical thought process for a human being trying to establish a baseline of security, but it is a complete and utter disaster for a firewall operating on machine logic.
Because of that first match principle?
Exactly.
The firewall receives a packet of data. Let's say an email trying to come in. It reads rule number 1, which is block all. It drops the incoming traffic right there on the spot.
It never even glances at the allow incoming email rule sitting gracefully at position number 2. The result is a total communication blackout. Nothing gets in, nothing gets out.
And that is a very quick way to grind a business to a halt and get a barrage of angry phone calls from your users.
Yeah, your phone will be ringing off the hook. To avoid that blackout, you can't just throw rules at the wall. You have to structure your rules correctly based on how the machine actually reads them.
So if the intuitive human approach of putting block all at the top fails so spectacularly, how are administrators actually supposed to structure this hierarchy?
Well, the best practice outlined in the Symantec documentation relies on a least privilege approach, built into a very specific 3-tiered architecture.
Okay, lay it out for us.
First, at the very top of the list, you place rules that block specific high-risk items. We are talking about known malicious IP addresses or specific vulnerable ports that have no business communicating on your network. You want those dropped immediately before anything else happens.
So you filter out the known bad actors first so they don't accidentally get swept up in a broader allow rule later on.
Precisely. Then, moving down to the middle section, you place your specific allow rules. This is where you carve out the permits for necessary business traffic. Your HTTP for web browsing, your DNS queries, your VPN traffic.
Okay, top is block the bad, middle is allow the good.
Right. And finally, at the very bottom of the list, you place your catch-all rule, which is block all other traffic.
So the admin's instinct to have a block all rule wasn't wrong. The placement was just upside down. It doesn't go away. It just gets demoted to the absolute bottom of the priority list.
If we connect this to the bigger picture, this specific structure ensures that your necessary, legitimate allowances are safely carved out and permitted first. Only after the firewall has confirmed the traffic isn't a known threat, and only after it's confirmed it isn't explicitly permitted business traffic, does that general block drop absolutely everything else.
It's a filter that gets progressively finer.
Exactly.
That makes so much sense when you visualize it as a top-down funnel. And understanding that sequential logic is absolutely crucial when we tackle our next big topic from the sources, which is the headache of VPN split tunneling.
Split tunneling is an architectural nightmare for security teams, and it happens far more often than people realize.
Let's define the stakes for you listening, especially if you haven't encountered this term before. Imagine our coffee shop scenario again. A remote worker is sitting there sipping a latte.
Doing some work.
Right, and they're doing the right thing. They connect to their highly secure corporate VPN. That creates an encrypted tunnel straight to the office servers, giving them access to sensitive customer databases. But at the exact same time, their computer's physical Wi-Fi adapter is still talking to the unsecured local internet at the coffee shop.
That is the split tunnel. Traffic is flowing securely to the corporate network, but also insecurely to the local Wi-Fi.
And the danger is that the person sitting 2 tables over with a packet sniffer could potentially compromise the laptop via that local public Wi-Fi. Once they're on the laptop, they can ride that secure VPN tunnel straight into the corporate network. The laptop essentially becomes a bridge over the castle moat.
It's a huge vulnerability.
So how does the firewall architecture solve this without completely disabling the user's internet?
Symantec has a specific best practice to prevent this, and it's a brilliant application of adapter-specific logic. By default, when you create a firewall rule, it applies to all adapters, meaning your physical Wi-Fi card, your Ethernet port, your virtual adapters, everything.
Everything across the board.
Right. To kill split tunneling, you go into your firewall policy and modify those middle-tier allow rules we just discussed. Instead of letting them apply broadly, you restrict them so they only apply to the specific name of the VPN adapter.
So if a standard firewall rule applies indiscriminately to everything, we are essentially forcing the firewall to differentiate the VPN traffic from the physical Wi-Fi traffic. How does that interaction play out in the rule hierarchy?
Let's say a user tries to bypass the VPN and browse the web using their physical Wi-Fi adapter. The firewall looks at that outbound traffic, it reads down the list and hits the middle tier where the allow rules live. But wait, those allow rules are now tagged as VIP access for the VPN adapter only. Because the traffic is originating from the physical Wi-Fi adapter, it does not match.
It doesn't match, which means the first match principle hasn't been triggered yet. So it falls right down the list, bypasses the middle tier entirely, and slams face first into that block all other traffic rule sitting at the very bottom.
Exactly. The traffic is dropped. Split tunneling becomes physically impossible at the network level because the firewall logic actively funnels everything through the permitted VPN adapter or drops it into the void.
It's an incredibly elegant solution. But reading through the implementation notes, setting this up requires a surgical level of precision. You can't just type the letters VPN into a text box in the software and expect the firewall to figure it out. How does an administrator actually define this adapter?
The sources detail the exact command line steps required. An administrator has to open a command prompt on a client machine and run the ipconfig all command.
Okay, ipconfig/all.
Yes. This pulls up the highly detailed configuration data for every network interface on that machine. From that massive block of text, you have to locate the specific virtual VPN adapter and copy the exact case-sensitive description string provided by Windows.
So if it says Symantec Virtual Network Adapter version 2.0, you need every single character of that.
Yeah.
Precision is absolute. If the casing is off by a single letter or there is an extra space, the firewall will not recognize the adapter and the rules will fail.
Wow.
Yeah. Once you have that exact string, you take it into the SCPM, the Symantec Endpoint Protection Manager console. You navigate through policies to policy components and into network adapters. You add a custom adapter, give it a friendly name, and paste that exact string into the adapter identification field. From then on, you have a discrete object you can apply your rules to.
But the notes include a massive warning about this setup. While we are restricting our allow rules to that highly specific VPN adapter, the documentation states we must leave our block rules set to all adapters. Why the difference? If we want everything going through the VPN, shouldn't the blocks be specific too?
That is a critical distinction that admins often overlook. You have to remember the physical reality of the machine. The laptop is still physically broadcasting and receiving radio waves on that coffee shop Wi-Fi. If a hacker on that local network tries to launch an attack directly at your machine, probing for open ports, for instance, you need your firewall to drop that malicious traffic immediately.
Oh, I see. If your block rules only apply to the VPN adapter, you are basically telling the firewall to ignore threats coming in through the physical Wi-Fi.
Exactly. If you restrict your block rules to the VPN adapter only, you leave your physical Wi-Fi adapter completely defenseless against local subnet-level attacks. The firewall would simply ignore the malicious local traffic because it wasn't coming through the VPN. So allow rules get restricted to force compliance. Block rules stay universal to maintain comprehensive defense.
That perfectly illustrates how you have to think about the physical environment and the virtual environment simultaneously. Which actually brings us to a fascinating nuance in the sources regarding a protocol called NetBIOS. The documentation dedicates a massive section to this, which seems odd for such an old piece of technology. Why is Symantec so intensely focused on NetBIOS for remote workers?
NetBIOS is a legacy protocol, yeah, but it's deeply embedded in the DNA of how Windows networks operate. It stands for Network Basic Input-Output System, and it's the protocol your computer uses for local network discovery and sharing.
If you've ever opened up File Explorer and looked for a shared folder or tried to find a wireless printer on your home network, you are likely relying on NetBIOS broadcasting to make that connection.
And it operates on specific ports to do that. Specifically, UDP ports 88, 137, and 138, and TCP ports 135, 139, and 445. The problem with NetBIOS from a security standpoint is that it is extremely noisy.
Easy.
Yeah, it's constantly shouting across the local subnet saying, "Here I am, who has the printer?" And historically, those ports are notorious attack vectors. You absolutely do not want NetBIOS traffic exposed to the open internet.
Which takes us right back to our remote worker in the coffee shop. If you are logging on directly to the public Wi-Fi, completely exposed without your VPN turned on, the sources are unambiguous. You apply the strictest possible policies.
Yes. In the Symantec firewall settings, there is a dedicated toggle switch labeled Enable NetBIOS Protection. For a direct non-VPN internet connection, you absolutely must enable this setting. When turned on, it automatically drops NetBIOS traffic attempting to enter your machine from external gateways.
It silences that noisy protocol.
It does. Furthermore, best practice guidelines dictate that you should explicitly create rules in your hierarchy to block local TCP traffic on those specific ports, 135, 139, and 445, just to create an impenetrable barrier.
So if you're off the VPN, you lock NetBIOS inside a vault and throw away the key.
Exactly.
But here is the massive aha contradiction from the documents. When you are connected via the corporate VPN, the rules completely flip. The documentation says you must actually go into your settings and disable the NetBIOS protection toggle. Why on earth would we lower our shields when connected to the office?
What's fascinating here is understanding what a VPN fundamentally achieves. When you activate that VPN, a secure, encrypted tunnel is created, and your computer is essentially transported, virtually speaking, onto the internal corporate network.
You're virtually sitting at a desk inside the corporate headquarters.
Precisely. And inside that headquarters, the entire corporate network relies on NetBIOS for legitimate day-to-day business functions. Accessing mapped network drives, finding those internal office printers, verifying domain controllers.
Ah, I see where this is going.
If you leave that general NetBIOS protection setting turned on while connected to the VPN, your own firewall will look at that legitimate corporate traffic trying to pass through the tunnel, classify it as an external threat, and inadvertently block it. You would cripple your own ability to work.
But doesn't disabling that overarching protection leave you incredibly vulnerable on the coffee shop side of things? We just established that the physical Wi-Fi adapter is still active and exposed to local threats.
It absolutely would leave you vulnerable if it weren't for the adapter-specific logic we just spent time setting up.
No.
Remember, we isolated all our middle-tier allow rules exclusively to the VPN adapter, and we put the universal block all other traffic rule at the very bottom.
I see how the puzzle pieces fit together now.
Yes. Any malicious NetBIOS traffic originating from the guy with the packet sniffer on the coffee shop Wi-Fi will hit your physical Wi-Fi adapter. Because it is on the physical adapter, it won't match the VPN-only allow rules. It falls straight to the bottom of the list and gets ruthlessly dropped by the block all other traffic rule anyway.
So you're perfectly secure from external local net BIOS threats without needing the general toggle switch,
Hmm.
which elegantly frees up the VPN tunnel to process legitimate corporate net BIOS traffic smoothly.
It is brilliant architectural design. The rule hierarchy, the adapter specificity, the protocol settings, they all interlock to create a system that is both highly secure and actually usable.
So we have spent all this time talking about locking down specific ports and tying IP traffic to distinct physical adapters. But humans don't think in IP addresses. We don't type a string of numbers into a browser. We think in domain names like google.com. How does the firewall bridge that gap? There is a setting mentioned in the documents called Enable Reverse DNS Lookup. What is the mechanism there?
Reverse DNS lookup is a feature that allows the firewall to take an incoming IP address and query a domain name system server to resolve it back into a human-readable domain name. So it translates an IP like 142.250.190.46 back into the domain it belongs to.
Why does the firewall need to perform that translation? If it sees the IP, shouldn't it just act on the IP?
Because administrators often want to create firewall rules based on domains rather than maintaining massive, constantly changing lists of IP addresses. For example, you might want to create a rule that says, allow all traffic to *google.com.
Right.
If you write a rule using a domain name, the firewall must have Enable Reverse DNS Lookup turned on. Otherwise, when the traffic arrives at your machine as an IP address, the firewall has no way to compare it against your domain-based rule. It will just ignore the rule entirely.
That sounds incredibly convenient from an administrative standpoint. You just type in the domains you trust and you're done. But the sources highlight some serious trade-offs regarding performance and security.
Convenience almost always comes at a cost in network security. If we look at the performance side, enabling reverse DNS lookup forces your computer to execute a DNS query out to a server for every single connection attempt that might match one of those domain-based rules.
So if the DNS server is having a slow day or the network is congested, what happens to the user?
The user experiences massive network latency. The firewall literally has to pause the traffic and wait for the name resolution to complete before it knows whether to allow or block the connection. On the security side, relying on external DNS servers opens the door to DNS spoofing.
Where an attacker compromises the DNS server itself.
Exactly. If they poison the DNS cache, they can trick your firewall into resolving a malicious IP address as a trusted domain name, bypassing your carefully crafted rules entirely. The Symantec best practice is very clear. You should always use specific IP addresses instead of domain names in your firewall rules whenever possible. It removes the latency, and it eliminates the spoofing vector.
That meticulous attention to detail brings me to our final set of sources today, which are the insights from Watchpost Security. Their motto is, protecting your perimeter with precision. Looking at their documentation, they don't just talk about lists of rules, they focus heavily on dynamic threat responses. Can you break down what they mean by mastering location switching and restricting lateral movement?
These are core concepts for modern enterprise environments. Lateral movement is what happens after an initial breach. A threat actor compromises one laptop, say, via a phishing email. They don't just stay there, they attempt to move sideways through the network to compromise other machines and eventually reach the high-value servers.
Right, they spread out.
Watchpost Security emphasizes using precision firewall rules to isolate client machines from each other, ensuring that even if one laptop falls, it cannot establish a connection to its neighbor.
And location switching.
Location switching is the ability of the endpoint protection software to recognize where the laptop is physically connected and dynamically swap out the firewall policy. If the laptop detects it is plugged into the corporate LAN inside the office building, it applies one set of rules.
Okay.
If it depicts it as at a hotel Wi-Fi network, it instantaneously switches to a much more restrictive set of rules. It is context-aware security.
What I found genuinely interesting in the Watchpost notes wasn't just the technical mechanics, but their emphasis on presentation. They dedicate a portion of their best practices to using exact, high-quality branding for their documentation, specifically a navy blue dark mode aesthetic, circuit board watermark backgrounds, and their official lighthouse logo.
Yeah.
Why does a highly technical security firm care so much about slide decks and watermarks?
It might sound like a purely aesthetic choice, but in enterprise security, clear, professional communication is a critical operational tool. When you are communicating complex topics like lateral movement restriction or location, switching to non-technical stakeholders or board members to get budget approval, visually precise and officially branded documentation builds trust.
It signals authority.
Yes. It ensures the technical precision of the engineering team isn't lost in translation when it reaches the executive level.
That makes perfect sense. You need political buy-in to implement technical solutions. Speaking of intense technical solutions, WatchPost Security and the Broadcom docs both touch on some highly advanced stealth settings built into the Symantec firewall. Things like TCP resequencing and OS fingerprint masquerading. How do these tools actually hide a machine from an attacker?
These features are essentially designed to make your computer invisible to automated scanning tools. TCP resequencing, for instance, randomizes the TCP sequence numbers of your data packets. IP spoofing attacks rely heavily on a hacker being able to guess those sequence numbers to hijack an active communication session.
So by randomizing them unpredictably, you effectively stop IP spoofing dead in its tracks.
Exactly.
And OS fingerprint masquerading. I love that name.
I like to think of it as a witness protection program for your computer. Hackers use automated tools to scan a network and identify what operating systems the computers are running so they know which specific exploits to launch. OS fingerprint masquerading alters the time to live and identification values in your TCP/IP packets.
So it alters the machine's digital accent,
Fine.
preventing the attacker's scanning software from figuring out if it's looking at a Windows, Mac, or Linux machine.
Exactly. But, as with the reverse DNS lookup, there is a significant catch mentioned in the documentation.
There usually is.
There's a massive catch. While highly secure, these stealth settings actively tinker with the fundamental structure of how network packets are formed. The documentation explicitly warns that TCP resequencing can sometimes cause severe compatibility issues with certain network interface cards, the actual physical hardware inside your computer.
And if the hardware doesn't understand the randomized packets?
The firewall panics. It interprets the confusion as a catastrophic failure and blocks absolutely all inbound and outbound traffic. You achieve the ultimate security by accidentally unplugging the computer from the internet completely. Total blackout.
Wow. It just shuts down. It really highlights why these settings are disabled by default and why administrators must test them rigorously in a sandbox environment before rolling them out to 1,000 corporate laptops.
Absolutely.
So to summarize the incredible journey we have been on today, we started by understanding the absolute top-down, first-match, sequential logic of firewall rules and why human intuition, like a block-all rule at the top, will ruin your day.
Right.
We learned how to completely kill VPN split tunneling by restricting our allow rules to a highly specific custom-defined VPN adapter while keeping our block rules universal to fend off local subnet attacks.
We also unpacked the counterintuitive logic behind NetBIOS protection, exploring why you actually have to disable certain security toggles when you are operating safely inside a corporate VPN tunnel to prevent your firewall from blocking your own legitimate corporate traffic.
And we weighed the convenience of reverse DNS lookups against the very real risks of network latency and spoofing, while admiring WatchPost Security's dedication to stopping lateral movement and ensuring their complex architectures are effectively communicated to stakeholders. For you listening, mastering these specific, intricate interactions is the true shortcut to building a network that is both functionally invisible to attackers and perfectly accessible to the people who actually need to use it.
It is a delicate, constantly shifting balancing act between usability and security. And frankly, looking at how intricate these static rule lists have become, it leaves me with a final, forward-looking question to ponder.
Go for it.
We've seen how advanced stealth settings like TCP resequencing and OS fingerprint masquerading can sometimes confuse a computer's own network cards into dropping all traffic. As we continue to build firewalls that are increasingly stealthy and complex to hide our machines from attackers, are we moving toward a future where our security systems become so paranoid that they inadvertently lock out the very legitimate users they were built to protect?
Now that is a paradigm shift worth thinking about next time you log on to a network. Thank you so much for joining us on this deep dive. Keep asking questions, keep looking behind the curtain, and keep questioning exactly how your technology keeps you safe. We will catch you next time.